Good morning, good afternoon, and good evening, depending on where you are located. And thank you, Chair, for introducing me. So my name is Groot Koerkamp, and in my presentation, I hope to inspire you with a systems perspective on technology development for the next level sustainable crop production systems.
I'm coming from the Netherlands, well known for the tulips, Mr. Verstappen, but also, of course, the water and the dikes and agricultural production, livestock, greenhouses, and of course also crop production. Coming from Wageningen University, where we educate bachelor, master and PhD students, but recently, since 2 years, also now engineering doctorates, a 2-year design program for technology development.
And coming to technology, the core of my presentation, and you see some nice examples what we've achieved in the last decade in the development of technologies to harvest fruits and milk and to manage weeds in the field without pesticides and hoeing machines, but also monitoring systems for animals to improve their welfare and health. And also in Wageningen, we work with many people on digitalization and future solutions for sustainable agricultural production. And you're invited to check our contributions on our website. And we all do that, of course, with the aspiration to contribute to the United Nations Sustainability Development Goals, to end poverty, protect the planet, and ensure prosperity for all in 2030. They also want to acknowledge the contribution of the Brundtland Commission, who coined the concept of people, planet, and profit, as well as the contribution of Michael Braungart and William McDonough, known from the book Cradle to Cradle, that inspired me a lot, and phrased it as how do we love all the children of all species for all time. And when it comes to sustainable production, we have to deal with a long list of sustainability challenges in our production systems, ranging from depletion of natural resources, phosphate water, to losses of emissions of nutrients and residues to the environment, which impact air quality, water quality, soil quality, but also labor is of course an important aspect, as well as societal challenges, animal welfare and health, but also societal acceptance and trust. In our approach to these challenges, we apply precision agriculture and digital technologies as the answer. And in short, we measure and sense soil, plants, animals, diseases, weeds, model all the process, make predictions, and based on that, we can give advice to farmers or have an automated actuation by a robot, by a robotic system, for example.
And the big question for me is, well, do and will all these digital technologies contribute to a sustainable food system worldwide, and will we reach up to the level that is needed? Or phrasing it a little bit differently and wider, how can we as engineering community contribute to our full potential to a sustainable food system as large? Yes, of course, I think we already do, and with our technologies, we have huge potential in our hands, but also time for some reflections. And I listed 7 of them. Starting with number 1, the big question, can we feed 10 billion people on this earth? And the answer is yes, as analyzed by the EAT Lancet Commission. But it constitutes a healthy diet from a sustainable food system. And it starts with a healthy diet, so which means we have to eat less sufficient, but in general less proteins, and especially less animal-based proteins, which have a relatively high environmental impact, which come from a sustainable food system, which not only comprises production, but also the whole food chain up to consumption And for example, it also includes the waste. 30% of all food is in the end wasted in the whole food system. But also it's about how is food distributed in the world.
And of course, it also includes sustainable production, where we produce food and many other things. But we have to be aware and acknowledge, but for who do we produce? Where is our consumer and what does he or she wants? And then it comes to the questions, what to produce exactly, where, how, and who. And be aware that more than 50% of the world population is fed by local and regional food systems, and exporting from our Western countries to these markets often disrupt those markets substantially.
We have to be aware that our digital technologies really focus on the optimization of our current food system. And there's a lot of focus on diseases, on problems, on weeds, which we don't want, and we are able to detect them, but we are hardly able to identify the related cause, and that one is seldom solved. And with all our add-on technologies, we really contribute to maintaining the current system as it is, and which hampers other bigger innovations. And there are also many lock-ins related to our current systems, how we have organized our production system, tilling in rows, how we deal with risks, the big machines we have with all the tires, the practice of plowing, how to deal with variation and disturbances, how the market is organized, all the implicities we're using bioscience and pharmaceuticals. And also PA and high-tech approach have their limitations, where we think that technology is the only and best solution to solve things.
While optimizing our current systems, we experience the negative side effects of certain improvements, often called trade-offs, or also result in pollution swapping, or, for example, also in higher costs. And with that, we never are able to come to the utopia point, which expresses the ideal status of sustainability of a certain system. And number 6, I see that the uptake and implementation of precision agricultural technologies and practices really hampers at farm level. Not only because of economics, but also because knowledge, skills and attitude of farmers do not match with the complex solutions as such. And also societal aspects of consumers and society play a role here.
And last but not least, we have to do with the democratization of technologies, which a field of social science which concerns about the availability and affordability of technology, the user friendliness, who was involved, who's accountable, and who, for example, is also the discussions about data ownership.
So with all these successes of technology that we've developed, we are now living in the bubble of the high-tech paradigm. And the paradigm is the set of theories, of rules, of explanations, of experiences and persuasions, how we look at reality, how we experience it, how we think what is normal and what is common, which means that we altogether think that better technology is good, technology is the only solution and is the way forward to improve the sustainability of our systems. And with that, we have created a kind of a digital technology hammer, and all challenges, all problems are perceived as a nail that can be treated with this PA hammer, so to say. Well, let me go back to my inspiration and my experience of the last 5 to 10 years, where I got more and more in contact with farmers, communities, which developed quite alternative ways of farming, organic farming, conservation agriculture, agroecological approaches, agroforestry, And nowadays we see more and more attention for regenerative farming. And these farming communities have developed methods and practices where they don't use or very hardly use pesticides, very limited inputs of fertilizers, and still very successful and achieve relatively high production levels in a very different way, and especially take a lot of care and attention for soil quality, and not only the chemical and physical soil quality, but also especially the biological soil quality. And that makes me and others really aware that, agriculture by heart is biology, is ecology, is complex and less predictable, gives uncertainties. And it's interesting to see how these alternative communities deal with that in a very different way than we do in our more traditional farming systems. And that gave me two important insights. First of all, that we have to recognize that our current systems that we have developed in the last 50 years are inherently problematic. We created very big fields with monocrops, go there with very big machinery, and we created the perfect environment for weeds and diseases to develop and spread rapidly and really explode in space and time. And with our big machines, we have compressed the soil, increased caused soil compaction, and with that really reduced the biological soil quality substantially. At the very other hand, we also learned that biological processes, ecology, can also prevent many problems and even solve problems itself without our direct interference. And what I learned is that, in these alternative systems, these communities apply more biodiversity, both in time and scale. And that made me aware that we need not only precision agriculture and digital technologies, but we also need a different approach and different technology to contribute to a next level of sustainable production systems. The next question is then, of course, how to come to a different approach and different technologies for sustainable crop production systems. Well, in our design approach that we teach and apply in our group, we always start with the Venn diagram, which is a diagram with all the system levels. And what you see here, it ranges from soil, field to farm and food chain up to world. And at every level, each level, you see the objects and subjects which are relevant there. So at soil level, you see the air, the organic matter, there's water, there are inorganic minerals, the soil particles, the nutrients, but also soil life. And at the field, there's of course the crops and the weeds, and the disease factors. And so we go higher up, and at every higher level, you see more stakeholders, people being relevant at that system level. And that brings me to the 7 challenges, and they all relate to these living entities. If you look at the lowest level, where the plants and animals are, and the microbiology in the soil, and then there's also the living soil, of course. Then there's the biotic and abiotic environment, which causes disease and disturbances from elsewhere. And we have to deal with farmers, consumers, society at large, and then in the end, we have to deal with all these living entities and stakeholders all together. And that brings me to 2 aspects that I want to address in the next slides. First of all is how to deal with, the stakeholders at the higher levels, at higher societal levels. Farmers, consumers, society. And what I see here is that we as engineers, we develop technologies from conceptual level to lab to prototypes, and finally get up to the technology readiness level number 9 when it's applied at full scale at farming practice. And while developing this technologies, we also have to deal, of course, with societal aspects and economic aspects. And what I see that is really a technology push. So we have to, later on, when we come up to higher technology readiness levels, we try to convince farmers, related parties, stakeholders, society, that the solution we choose as engineers is good, it's the only solution, is the best solution. And also we have to deal with the economics, how to make a solution economic viable. But the question is, of course, that's a lot of push. How can we convert that? And could we convert it from a push to a technology pull? And could we start from the real needs, wishes, demands of the societal stakeholders, consumers, farmers, technology suppliers? But also, could we start from economic limitations and possibilities, and take those into account when we develop new technological concepts at a lower level, before we develop it up to a high level. So really, can we convert this and take that into account? And I think that will, can really be a complete different approach instead of the technology push approach. Then if we look at the lower level, we have to deal with the biology, the ecology of the plants and viruses and bacteria and microorganisms, with all their unpredictability, external disturbances, etc. And what I see in our current approach is that we use a technological approach there to deal with these complexity, unpredictability of all these ecological processes. We try to keep disturbances outside of our systems, and when they get in, we measure, we want to kill them, we want to minimize it, so we overrule all the ecological processes. And with our monocrop systems, we have really reduced the complexity of the soil and the crop and plant interactions to a minimum, so that we think it's easier to manage. And also here, we could ask ourselves, hey, could we also reverse this relationship? Could we start from the ecological and biological processes? What's going on? How could ecology and biology contribute to a sustainable food system? And what would that mean for the technology and solutions that we develop as engineers? We tried to summarize that in this picture, also thanks to my colleague Eldert van Henten. So we do typically see in our current systems that technology controls ecology. We have monoculture systems, both for plant production systems as well as for the animal-based systems. They're simple, there's a little complexity, uniformity. We strive for uniformity and keep disturbances out. Well, we've already seen and learned that, hey, if we start from the needs of plants and animals, that we can better serve them and can design better systems. For example, very welfare-friendly roundel systems for laying hens, but also intercropping systems where we can support and enable plants in their development and growth. But the next step could really be, well, how can technology collaborate with ecology and have mutual beneficial interactions? How can we really start and from the ecological processes? And that's expressed here for the plant systems with a pixel farming system. And for animals, I have two examples that I want to elaborate on a little bit more. And that's what we call technology for ecology-based farming. So what we developed in the last 10 years is the concept of animal capacities, and how can we use those capacities to contribute to our goals as managers, owners of our production systems. And the example of pigs relates to the development of a pig toilet, where we train pigs to defecate, to urinate on a very small spot to reduce emissions of ammonia, odor, and contribute to high value nutrients for crop production. And the example for laying hens is the dust bath unit, where we really lure the animals, the laying hens, into the unit where they can dust bathe within a unit which is enclosed, so that the dust that is the fine dust that is generated remains within that unit. And it is driven by the demand and wishes of the laying hens. And the challenge is, how can we convert that concept of animal capacities to plant and soil capacities, and use functional traits of plants and ecological systems to contribute to our sustainable production goals and functioning of the system. Well, I have 3 examples to further elaborate on this. For example, for disease management, where our current approach is really to early detection and kill diseases and factors, where we could also shift to intercropping systems that prevent rapid development of diseases, but we can also use natural enemies which need also support, for example in flower strips in the field. When it comes to nutrient exchange and supply, we really think, okay, in our current approach we have precision supply of nutrients, but we could also think, hey, how could we use the soil as a buffer that can also transport and make nutrients available to the plants whenever they need it. And there's more and more evidence coming up that all the mycorrhiza and the food web in the soil can contribute to support nutrients and water for our production plants. And that also relates to the third example. So instead of precision irrigation, could we shift to more natural approaches where we prevent soil compaction and with that enable deeper rooting of the plants, but also have other plants, for example trees, that can really root much deeper and with that contribute to the water sourcing at deeper levels and supply that to other plants in our production system. Coming to the end of my presentation, the question is, of course, how can we start and enable this approach of technology for ecology? And the first step is, I think, is to forget that we can, as engineers and farming community, control all the biological processes in the systems. We have to step back there a little bit. And instead of solving problems, we better focus on preventing problems. So design and operate the system from a different starting point and focus on health of plants instead of diseases. How can plants maintain their health themselves within a certain environment and ecosystem? And let's trust nature more and use the variation, diversity, and complexity for our goals, for our production goals, instead of getting to very simplified monotonic systems. And technology, especially the big tech, high tech, is seen as a kind of enemy by ecology-based farmers, and it's a real challenge how to convert that to that technology can also contribute to those kind of farming systems. Last but not least, what also will help is that we not only focus on the economic aspects of the crops that we till, but also think about how can we profit from other ecosystem services that we provide with our agricultural systems. Well, have a look at our website, Technology for Ecology, where we elaborate on current projects on this topic. Well then, some take-home messages. First of all, I think that precision agriculture and digital technology are not the only holy grail to sustainable production. And sustainable solutions are not per se high-tech, and vice versa. Not all high-tech solutions contribute to sustainability. But what I see is that in the T3 approach, the new solutions are very knowledge intensive. And not only from an engineering perspective, but also we need biologists, ecologists, but also social scientists to develop a new generation of farming systems. Let's start from this T3, technology for ecology-based approach, and that's still a process of learning by doing. But what's quite clear for me is that it needs new knowledge, new perspectives, new attitudes, and new skills for many people to develop this concept successfully. And with that, I think we can, work on and contribute to a next level of systems engineering in agriculture. But with that, I'd like to thank you for your attention. And if you're interested to follow me and contribute or work together on this concept, you're very welcome to further explore the potential of technology to improve the quality of life together. Thank you for your attention again.